The migration to post-quantum cryptography, it's a must-do. It's absolutely non-negotiable. It needs to be done. Historically, the Shor algorithm, that is like the one that when will be implemented on scale, will lead to the break of RSA encryption.
Our guest is Marco Marcozzi from the University of Vilnius.
Yes.
And I assume originally from Italy.
Yes, you're correct.
Judging from the beautiful name. And you work at the intersection of quantum mechanics and pharma, in a sense. Could we say that?
Well, that's one application that we are exploring. In practice, what I'm working on is the intersection between machine learning approaches and quantum computing.
Okay, and that touches pharma, distributed systems?
It touches in our recent works is touching pharma because it's one of the fields that might benefit the most from the interaction with quantum computing. But the future is.
But have you touched other fields than pharma as well?
Yes, we do also do research in optimization for logistics, for example, or like energy management and logistics.
Okay.
So, but the field on which at this moment I'm focused, yes, it's quantum chemistry, pharmacology.
Okay. But would you say we can describe it something like what can quantum build, and not just what can quantum break, in a sense?
Absolutely. That's exactly the point. Yeah. The point is that which are the fields or like applications for which quantum computing is actually useful or will be useful in the future. But we already say that there are some small problems or like some specific problems for which quantum computing, and specifically in our case, variations of like quantum machine learning techniques are useful to build and to foster like
what would give us maybe some concrete example? Maybe?
Yes, so there is numbers now are difficult to say, it's you need papers, but let's say that there are like papers like in literature already like reviewed and published that are increasing some metrics of efficiency, or like, I don't know, I can give an example in fraud detection. There is about like 10%. Again, proved it depends, but 10% increase in false positives. So for the field of finance is a great thing, because you need to scale down the human work of reviewing these false positives. In pharmacology, it seems that especially for quantum chemistry, quantum computing, it is the way of doing it, because it's naturally quantum. Again, I cannot say numbers now, but it's at least promising in these aspects. So,
and your poster talks about it.
Yes, and my poster is working. It's talking about this, and what can we say? We didn't get results that are at this moment better than the classical ones, or at least we cannot prove it. But there is room for improvement. This is like a first prototype. In this field, it really is like similarity measurements of molecules. There is not much published yet, so it could be one of the first approaches that we propose, and hopefully develop more and go deeper.
Just for everyone, the paper is called Quantum Shape Similarity for Drug Discovery.
Yes, that's
okay.
So the idea is that molecules, have different atoms, and different molecules, in principle, have different pharmacological effects. In some cases, there is like substructures or like some active parts of the molecule that can be found in different molecules, and this should have, in principle, similar pharmacological effects. So the idea is that when you know one molecule that maybe is having a patent on or something, and you want to find something similar, you're finding a molecule that has a similar shape, and testing if it actually has the similar pharmacological properties. That's very, very rough idea. And
It's maybe like fitting a key into a lock.
Yes, actually, yes. It's a very good. Yes, it's a very good image to explain the idea. So, but it's one key, so the pharmacological effect, and you're finding another. Sorry, a keyhole.
Yeah.
One keyhole is like the pharmacological effect, and you're finding a key similar enough to actually open it.
Yeah. And that would be the molecule.
Yes, the other molecule.
Yeah.
And one of the problems is that the databases where these molecules are like stored, they are like huge. It's like millions of entries, and you need to scan all of them.
Yeah.
In principle.
Yeah.
So this is like a big computational task.
Yeah.
And we're hoping that by making faster the scanning of each molecule without needing of rotating them like by hand, let's say like this.
And tell me, what is the difference maybe from a quantum computer perspective towards a classical computer?
So from a classical perspective, as I said, you need to rotate the molecule according to some rules and make them overlap. Almost by hand. Of course, there is machine learning approaches that are doing this almost automatically, but this is computationally intensive in any case. And to make a learning algorithm for this, it doesn't seem really a good way to proceed. You cannot really learn like molecules in a way. We're actually thinking about if it's possible.
Okay.
So this is the classical part. It is very intensive in terms of computation. Sometimes actually the overlap is not good, so you need to, like the automatic one, you need to adjust it manually, and it takes a lot of time. So our idea is that you can encode a lot of features of the molecule, not only like the spatial geometry, but which is actually what the poster is talking about, spatial geometry of the molecules, but also other features like the atom size or like the atom type, electronegativity, other features like global features of the molecule and not of the single atoms, and in a very efficient way. So like compressing all this information into a few qubits. Let's hope so.
And maybe just, I know that you said numbers are hard to talk about without actual the poster or everything, but just for me to get a grasp, are we talking about millions of possibilities, trillions, 10 to the number of 26 possibilities? I mean, that's a big difference, right?
So if we're talking about a specific problem, so let's say two molecules of the order of 20 atoms, we have 20 factorial possibilities of pairwise comparison between them. If we're doing pairwise comparison, for example, between atoms, which is the case if in some approaches. We didn't go through this route because 20 factorial, even if you're making them as a superposition, which is difficult, it gets noisy. So we found like a classical pre-processing to find a good starting point, and then we optimizing on it. So finding, let's say, the ground state of the overlap.
Any specific optimization algorithms used? Or?
So quantum machine learning as now is a hybrid approach. So we have a quantum circuit, quantum algorithm that does a certain part of the task, and normally a classical optimizer to find the gradient of the cost function, or like, mostly that. So in our case, we used a derivative-free algorithm, like Cobila, I think it's Cobila called. So it's like having linear approximations of the gradient function.
Okay.
So you don't have to provide the gradient function because we don't know it.
And like if this would work, this would obviously be like something like holy grail for pharma, right?
Well,
I mean, it's not if this would work, but like if it becomes industrial scale.
One day when it will be the industrial scale, and we can prove that actually it's much more efficient using a quantum computer. Well, yes, definitely, because you can test a whole database of possible candidates for finding your key in maybe exponentially faster, but I don't, you know, I cannot say. I cannot say. But that would be really the holy grail. That would really be.
And that would potentially then accelerate development of.
Absolutely. That's the ultimate goal.
Got it. And where do you think the restraint comes from currently? From the hardware, from the algorithm, from the physics itself?
At this moment, it's obviously the hardware. That's the hard bottleneck that you know, we need to accept for the time being. But it's also true that better algorithms will give also better results in principle. So now, as I said, this is our first proposal. We already start thinking how to improve it, because we know that there is.
And it's one of the few, just for maybe the audience to understand, it's one of the few posters which actually touches real world applications in that sense.
Yes,
I mean, we have been yesterday to the poster sessions, and it's very theoretical, and it speaks about frameworks for finding algorithms in some cases, but it's very, very, very theoretical. And this one is one of the few posters which actually gives you a real world
Yes, if I can add on this, actually, because our idea is that, yes, to develop algorithms that are like probably better than classical one would be amazing, and it is amazing in many cases. But now we are also trying to solve like real world problems. So given a problem, find an algorithm that right now would work. It's what we're trying to do. That's also another reality, is that we don't really have access to, you know, commercial grade quantum computer now, so we're doing mostly simulations for now. But there is time also to implement in real hardware.
And this kind of seek and match problem, I don't think it's just a problem of pharma, right? We see that problem in other industries as well, I think, and maybe touching your background of cross-pollination, do you see other areas which could profit from something like this?
Absolutely, yes. As I said, logistics and like logistics of energy, it's one of those. Finance can benefit very, very much from this, because optimization is one of the tasks that quantum computing possibly can do better and or faster. It's double-sided, either better, either faster. Best will be if both. Than classical algorithms, for example, in portfolio optimization, or I don't know, as I mentioned before, fraud detection, and other fields could be also healthcare. There is part of my group, research group, that is also investigating how to speed up, how to say, the finding illnesses into like healthcare images. It's done classically with the machine learning approaches. We're trying to see if quantumly can do it better.
And I mean, this kind of reminds me also, in the world of encryption, of breaking keys, right?
Yes, that's the other side of the of the coin. As actually you well said, we're not trying to break.
I mean,
we're trying to build. No, but that's actually a good point. You know, we are trying to build using this technology, like breakthroughs, right?
But I mean, from my understanding, in a sense, this all goes down to some consensus, right?
No, I think it's really just a matter of interest. You know, historically, the Shor algorithm, that is like the one that when will be implemented on scale, will lead to the break of RSA encryption and, like, you know, all these problems on factorization, large number, and the discrete logarithm. It's what actually sparked the interest of, well, let's say, wide interest of the researchers. Before, quantum computing was, how to say, a party trick maybe. In this case, instead, they found a real-world application in the 1995, I think, something about in the 90s in any case. So that's how now we're here talking about this. So, you know, it was surprising, I guess, at the beginning. I cannot say, no, I was a child at the time. But yeah, that's a matter of perspective. That was one discovery that could have or could lead possibly to
But can quantum build a better consensus mechanism?
There is research actually on this.
Yeah.
My experience to the PhD was actually about consensus
That's
in classical, in classical settings, in classical distributed systems. I was trying to find what is like the state of the art of quantum consensus, whatever that means, and actually trying to define whatever that means.
Yeah.
But I put a little bit aside because it's such a vast field of possibilities, at least, that maybe it takes a whole career to
maybe to dive a little bit more deeper into that.
Yeah,
maybe tell us what were your findings.
So, for example, a very good example that I know is the Byzantine fault tolerance.
That's just for everyone to understand. That's the main consensus algorithm used by the majority of distributed systems and blockchains, which are proof of stake.
Well, yes, it's based. Well, yes.
Yeah.
It's true. Well, but if we're considering, for example, Bitcoin, that is the most known, that's a different one.
Exactly.
Let's say all the ones that are more caring about actual, how to say,
programmability.
And fault tolerance of the system.
Exactly.
Because again, Bitcoin is on sheer numbers of people that is participating. In this case, instead, you need to have a certain set of participants. But enough of the classical part. There is a quantum algorithm, or like protocol, I will call it, that is quantum Byzantine fault tolerance. And how to explain? I would not say this is better, but it's different. And so the fact that you can think how to secure systems or like distributed systems using quantum phenomena, it's fascinating. Now, on the utility we can discuss, but it is fascinating. So,
but that's like when people say quantum consensus or quantum in the context of distributed systems, blockchains, whatever, they always talk about the risk of the breaking of the encryption, right? But here we are not talking about the risk of breaking encryption. Here we are talking about how do we fundamentally create a new network of distributed computers around the world, nodes, whatever, which have a new consensus mechanism which utilizes some quantum properties.
You're absolutely right. Yes, this is not about the encryption of the voting system or like finding whatever numbers you're trying to find. This is about how to establish, I would not say trust, because it's not about trust even between, actually it's quite the opposite, between nodes, but how to establish trust in the network, that the network is working, so we trust that the actually is working properly.
And do we use something like entanglement here?
Or? In the original proposal, it was use entanglement. I think, but you got me on a spot that I'm not sure honestly at this second. This was like 4 years ago. Interest, of course.
But I mean, it could. I mean, I could imagine it could have some properties of quantum geometry at least.
Yes, this is true. But about entanglement, unfortunately, I don't remember if the original paper was proposing it.
And for someone who is in this field today, would you advise that is a field worth exploring?
Yes, absolutely. Of course, it needs passion, because it's passion and patience. Because there is. It's very active. It's a lot of things happening. A lot of new discoveries maybe every day, but sometimes it takes really patience and that you believing in what you're doing.
A lot of sleepless nights to write.
Sometimes, but to believe that one day you can actually really implement it. Because we are really doing like a lot of simulations, a lot of theory. In some cases.
And I would say we are constrained by the hardware in most cases.
And the hardware is one of the hard constraints that we're not dealing with, and so.
And maybe generative AI in quantum. What do you know about that?
So that's
enlighten us.
That's a tough spot in the sense that It can be used. There is companies actually that are trying to use AI for quantum. So how to
That is
make,
what we learned about.
Yeah. So
in the
it's
morning,
like,
Google, admitted that they
yes,
use AI.
yes. So it is like how AI, or in general, can help optimizing processes in the quantum information processing. Sorry for the pun, but that's what it is about. So how do we optimize and actually maybe secure, or like better scheduling of the hardware? It's all these kind of things. So this is a real part. The generative part of AI, I think it's more about other things.
What would be like a quantum diffusion model?
So that's also an interesting part, but this is going into how to explain how to again process information. So that would be one of the ways of, for example, doing classification. It could be so you're doing you have some plain text or like plain data. You like obscuring it, obfuscating it with some noise, and then try to learn how to defuscate or like to denoise these data sets. This is actually a very interesting aspect. With part
and for
of
that we need our optimization algorithms.
Yes, but
and can we use some of the
that's what I want to. Yes, you can use some classical approaches, or hybrid classical approaches, which is actually what for now looks the best.
Promise,
most. Because of the hardware constraints for the classical, for the quantum.
So in a essence, we could say the next maybe years will be defined by hybrid models for now.
Yes, it is defined right now. It's the one that are actually bringing something really to the table for now.
But once we, let's say, reach planetary scale, quantum internet, or planetary, like something like bigger quantum computers or quantum
It's not
networks.
about bigger, of course, also, but when we will be reaching fault tolerance, we will not need anymore to have hybrid models.
What's your take on the fault? When I always ask this, sorry. One of my questions is like, when do you think we will reach our fault tolerance?
It's always 5 years away.
But then, okay, maybe follow up immediately after that, because no one really can say what changes once you get it.
Well, practically everything, because we don't have really to worry about how we make the algorithms suitable for the hardware, but just how to make better algorithms. And this is one of the approaches that actually we are following. So we're trying to forget that we have a hardware constraint and see what would be the best approach. But most of the time we need to scale down and try to understand how to...
And once we have a fault-tolerant quantum computer, which is a big undertaking, and a lot of components are going in there, and a lot of researchers and builders are trying to achieve it. In a sense, would you say that classical computers will lose relevance in that?
Absolutely not. We will never get rid of our classical computers, because many tasks are just as efficient as they can be on a classical computer. And quantum computer will be a helper, I don't know, like a subroutine of some tasks. And that's what will be. And that's how it should be. We'll never have like our quantum phone.
Unless we find some superconducting.
No, but because it's not useful. That's the point. Because some tasks, for example, I don't know, image processing for like, it's done perfectly on GPU. And so no. This is actually one of the first things that normally say when doing introductory like talks or like lessons. Don't
expect a quantum computer phone by Apple.
But because it's but because it's not necessary. Again, for our knowledge at the moment, one day we don't know. But for our knowledge at this moment, absolutely not. Actually, it's a very, very trustworthy companion for developing quantum algorithms and quantum technologies in general.
Maybe to go more deeper into Vilnius, the Baltics.
Yes.
How do you see it compares in the Baltic region or Europe, the European Union, compared to maybe the Americans or the US? How do you have intersections?
Well, intersection, yes. I mean, we are interconnected. We have colleagues, partners. All over Europe. For now. For example, like the poster we're presenting, it's in collaboration with some researchers in Almeria University in south of Spain. And so, how the Baltics are entering the global picture? There is a lot of potential. I think that especially I'm talking about Lithuania and Vilnius, we're lagging a little bit behind in terms of algorithms. We are the first group that is full-time working on quantum algorithms, and we started a couple of years ago. So on this we are lagging a little bit behind, but there is a lot of potential and a lot of brilliant minds that like I'm talking about students that want to get into this.
Yeah, and I think more people will try to come into the field because it's such a vast, expanding, unknown in many fields. And here, if you walk around, you meet astronomers, you meet computer engineers, you meet all sorts of people.
And on this, actually, speaking of what we just said before, it could be just an interest of like a classical programmer of knowing that you actually can do some specific tasks better on a quantum computer, and just when you know and where to get to look into it. Maybe already just pre-packed solutions, it's fine too, but that you need to know.
Yeah, and that is a good way maybe to close our session is, do you think we are working towards one killer application, if you want to call it that, or like a defining moment of quantum computing, as I shared previously, like a global quantum network, or like one killer feature everyone will use? Or do you think it's the small wins, many quiet domain-specific features, which will then lead to success?
So for now, I think we need to take the small wins.
Yeah.
Of course, the hope will be to have, a quantum internet for, mathematically secure networks.
Yeah.
Because that's what's about, quantum internet, practically.
I mean, that's probably what everyone is working towards.
I don't know about killer application. I think it's more about finding where we can actually make a difference in terms of accuracy or in terms of speed. So whatever field will actually fit these requirements, different problems that are difficult to compute classically, problems that actually don't require too much data, because still, even when we'll have a big quantum computers, it will be much smaller in terms of space than a classical one. And technological advancements in terms of like quantum memories, all these things. There is a lot of things that need to come together.
When we touch speed, we are also touching the notion of time, right?
Yes.
And speed highly correlates with time, as we all know. So what do you think about the time difference happening in quantum space, in classical computing, and maybe without a computer? And how can this maybe change maybe our perception of time at all?
Oh, that's a very philosophical question.
Yeah,
well, I mean, if we're taking a really high level of philosophical, thing, well, quantum theory is a little bit already reshaped the concept of time. Obviously, the real reshape was with the relativity, general relativity. Again, it's not my field. This is really like theoretical physics. But
you could just take your personal opinion.
My personal opinion that if we'll ever solve the unification of quantum theories and relativity, definitely we'll have a different concept of time. Well, most likely a different concept of universe. Yes,
a better understanding, let's say.
Yes, but that's the real holy grail of the theoretical part. One of them, honestly.
Of course.
But yes, I don't know. From like applications or like I would say, now it's coming this new term of quantum informatics. In some fields, now someone start using it. So let's say that we're doing quantum informatics at this moment, because actually I'm working in the faculty of mathematics and informatics.
Yeah.
So that's.
I mean, in many cases, these fields cooperate.
Yes, of course, we need to have interactions and inspire each other.
I mean, we wouldn't have many of the algorithms without the mathematical side, obviously.
I mean, the algorithms until, I guess, a few years ago, I cannot say a number, they were all mathematical proofs.
Exactly.
So now we start, as I was saying, we are trying to do the opposite. We are starting from a problem and trying to engineer that's it, a solution on top of that problem. Before it was, there was like very general problems, mathematical problems, the factorization of numbers, or like searching around structured database and what we all know. Now instead is like very specific tasks. In this case, like in my case that we're discussing is like how to measure the overlap between two molecules, like spatial overlap. There is plenty of ways they can do it, and we're trying to develop one. And then, trial and error, make it better.
So basically, maybe as a closing thought, we shouldn't look at quantum as something which will break the world and people have to be scared about their data or their security, but more about that it opens a new frontier of building good stuff for people.
But on this, I want to make a remark. But we need to be aware of the possibilities, of the possibility at least. So, for example, like migration to post-quantum cryptography, it's a must-do.
Would you say this is non-negotiable today?
It's absolutely non-negotiable. It needs to be done. I mean, that's reality. Because maybe we will never be able to implement, and I hope that is not the case, that to implement like a Shor algorithm so, like in a quantum computer so big that could actually break this kind of encryption.
I think that is highly unlikely.
I know.
I mean, almost impossibly unlikely, considering the fact that hardware acceleration is undergoing.
So that's the thing. But let's see it as a possibility that is not going to happen. But regardless, that is not. Since we know that there is better algorithm for encryption, why should we not do it?
Exactly. And there's also better algorithms potentially than Shor's.
Well, absolutely. We still didn't discover it yet.
Yeah, but like people are actively researching.
That's a very good point. And who knows, maybe someone one day will discover a classical algorithm and break the assumption that P is different from NP, we don't know. So we need to be prepared.
Exactly. So and what would you advocate for, a lattice-based encryption scheme everywhere?
As I said, we need to be prepared. And we know that the assumption on the lattice-based schemes, again, it's not my field, but I have a little bit of experience. We know that the assumption are much stronger than the one on which RSA, for example, is based. So why not use it? Yes, there is like constraints on the memory and on the size of the keys and everything. But
But that's optimization.
That's optimization. Yeah, it's like engineering of the data.
And solvable today. So everyone should do it.
Yes, absolutely.
Okay, Marco, that was super enlightening. Thank you so much.
Thank you for inviting.
You're welcome, most welcome, and we will visit your poster session.
I'm waiting for you.
Thank you so much, Marco.
Thank you.